Hey folks, how y'all doing? We're going to start looking at a real hash system today. We looked at it sort of a baby one last time. We're going to get to a real one today. Before we do that, we're going to start with something called the random oracle model. So we talked last time about what a hash family is. We have a set of possible messages, set of possible message digests. These are the hashes that are created for the message. This is going to be a large set. This is not a small set. This is going to be still very, very large. So I'll just say larger and large. But there are many, many, many more possible messages than there are message digest. So, for example, one of the schemes that we're going to be looking at produces digests that are 160 bytes long, not bytes, 160 bits long, which means there are 2 to the 160 possible digests, but it allows for messages that can be, millions of bits long. And so the number of possible messages is in the order of 2 to the millions, which is even much, much larger. And so this is a large set, and this is a much, much larger set. And then we have a set of possible keys. We want this to be large also, so that the key is hard to guess and it can't be brute forced. And then we need a function then that matches the text using the key to a hash. And so there'll be a function for each key, basically. All right. So we're dealing with huge sets in this process. We want the functions to be fast to compute, and then we want these 2 kinds of resistance. So we have a plain text, we have a key, and then we have the digest, which we also sometimes call the hash, and we sometimes call it a signature. All right. So the idea is that if we know, so pre-image resistance is that if we know what the digest is, so if we know what the output Y is, we don't want to be able to create 2 plain texts that create that same digest. So if I know what the digest is, I don't want to be able to create a plain text that I don't want to reverse engineer it to a plain text. Even if it's the wrong one, because if I can create the wrong one, then the wrong one and the right one form a pair that has the same digest. And so if I know what the digest looks like, I don't want to reverse engineer it. That's pre-image resistance. And then collision free is even if I don't know what the digest is, but I know what the plain text is, I don't want to create a second plain text that shares the same digest. I do not want to ever have this situation where I know 2 different plain texts that share the same digest. It will happen because the set of plain text is larger than the set of digests. But it should not be something that we can plan on, that we can engineer, that we can by reverse engineering create a plain text to do this. If it happens, it should happen as an entire random accident. So, which gives us this model here. This is a theoretical hash function. It's not a real function that has all 3 properties that we want. And so here's the function. There is a supernatural oracle that when you ask the oracle a message, the message will choose a random digest and return that value instantaneously. That's where the fast comes in. And the oracle writes this pair in a large book so that if somebody ever queries the oracle with the same message, the oracle will not give a random value, but will give the previously chosen value of y. So every time you ask the oracle for a message, it gives you a random answer if it's never seen that message before, and if it has seen that message before, it gives you the one that's there before. Because the behavior of the oracle is random, it can't be reverse engineered, and so we can't create pre-images for a key and collisions. That's the idea. So does it exhibit the three desirable properties we've discussed? Yes, it's fast because, in fact, it's instantaneous. And pre-image resistance and collision resistance we have because the behavior of the oracle is random. And so we cannot reverse engineer this process. So is it possible for a non-theoretical hash function to improve upon this model? So there's one thing we have not discussed yet. When we say the oracle chooses a random y, the question is, how big is the pool from which the oracle chooses from? This is important because if the oracle is choosing a random y by just picking from a small set, then even if the behavior is random, we can duplicate it by trying enough just guesses. That if the oracle only chooses from 5 possible hashes, then we could try, we might not actually get a same match in 5 guesses because we might get a repeat, but we'd probably get the same. We'd probably get a collision in, say, 15 or 20 guesses. So that's the idea. And so a non-theoretical hash cannot improve upon the speed because you can't improve upon instantaneous. And the only way to improve upon the resistance is to use a much, much larger key space. And so only by using a much larger space or hashes. What the specifications call y. If I go back to this slide, y is the set of possible digests. If our non-theoretical function chooses from a much, much bigger pool, that's the only way we can improve upon this model. Okay? So let's talk about the size of the pool and how that affects the security here. So let's say the size of the pool is m. So we have only m possible digests that can be chosen from. And we're going to try to generate a collision by generating Q messages. We're going to query the random oracle every time we get a message and see if 2 responses match. So what is the predicted success rate as a function of Q and M? Okay. So we generate message 1. Okay, so we have message 1, and then we get the hash back from the oracle, which is Y1. And so far, we don't have a collision. So chance of collision is 0. Because right now we do not have a collision because there's only one message, and we have to have a second message for it to collide to. So let's look at the second message. X2, the hash is Y2. And the only way that we can get a collision is if we chose randomly exactly the same value we came from the previous hash. So the chance of collision is 1 over m. All right, so then let's look at message 3. So we get a message and then we get a hash. And now the chance of collision is we have a 1 over m chance that y3 collides with y1 and a 1 over m chance that y3 collides with y2. And so the chance of collision is 2 over m. And so on and so forth. By the time we get to the last message we generated, message Q, and hash is YQ, the chance of collision is Q minus 1 over M. When I say the chance of the collision is the chance that this specific message is colliding. The total chance of collision will be the sum of all of these possibilities. Any one of these messages can collide. And so the total chance of collision is the sum as I goes from 1 up to Q minus 1 of I over capital M. But there's something we can do with this formula that we'll look at on the next slide. Okay? All right. So, all right. So the chances of not getting a collision is, let me explain this a little bit better, because I want to make this clearer before we go on to the next slide. The chance of getting a collision is the chance that we collide here or here or here or here or here. And because we're taking an or statement, we're going to sum these together. The chances of not having a collision is, so the total chance non-collision is the possibility that we don't have a collision here, don't have a collision here, and we don't have a collision here, and we don't have a collision here, and we don't have a collision here. And that's a multiplication problem. It's 1 minus I over M, and it's a product from I equals 1 to Q minus 1. Okay? And so, because this is now an and statement that we are negating all these things happen, so we cannot have a collision here, and we can't have a collision here, and we can't have a collision here, and so forth. So what we're going to be doing is, this is the product, which is the chance of a non-collision. Okay. But we're going to make an approximation here. If M is large, and so 1 over M is a small number, then squaring a small number makes it much smaller. For example, if x is 10 to the negative 6, then x squared is 10 to the negative 12, which is much smaller. And then x squared over 2 factorial is even smaller than that. And so if x is small, these numbers are going to be very, very, very small. And so these two values are approximately equal because they're the same number, but one is plus a very, very small amount. But this is this infinite series for e to the negative x. And so if these fractions are small, 1 over 1 minus m, 1 minus 2 over m, times all the way up to q minus 1 over m, it would be approximately equal to e to the negative 1 over m, e to the negative 2 over m, so on and so forth. But we can simplify this because we're multiplying a bunch of things with the same base. And when we multiply things with the same base, we're adding the exponents. And so here's where we get a summation, even though we're looking at a product here. So this is e to the negative 1 over m times the sum up through q minus 1 of I. And there's a formula for that you may have seen before. It's q minus 1 times q minus 2 over 2, which is e to negative 1 over m times q squared minus 2q plus 2 over 2. Okay? So now if q is so small that even when we square it, it's still very far away from m. Okay? And so if m is much, much greater than q squared, this is the important thing here, then this numerator is going to be tiny compared to the denominator. And if a fraction has a small numerator and a large denominator, this fraction is going to be close to 0. And e to the 0 is approximately 1. And this is important, that in order for the random oracle model to work, in order for somebody to attempt to produce a collision by just flooding the system with lots and lots of messages and hoping for a collision, then we have to ensure that the size of the possible digests is much, much larger than the square of that possible value. And so, an example, if we anticipate that an attacker might just try to flood the system, and maybe they can flood the system with, let's say, 1 trillion messages. So we could expect as many as 10 to the 12 messages. Then we need for m to be bigger than 10 to the 12th squared, which is 10 to the 24th. And we need it to be bigger by a couple of orders of magnitude so that this fraction is close to 0. Making it a tiny bit bigger doesn't work. We need it to be significantly bigger. So, like 2 orders of magnitude, if say m is approximately 10 to the 26, a message size, message spaces of this size would only give this fraction to be approximately 1 over 10 squared, which would be a 1 in 100 chance. We might even want some more security by making this 10 to 27 or 10 to 28, which would make this 1 in 1,000 or even 1 in 10,000 chance of succeeding. So, but we need for m to be greater than q squared by at least a couple of orders of magnitude. That's the idea here. And like I said, we're looking at a hash system where the message size is about, 2 to the 160, which is roughly about 10 to the, since 2 cubed is 8, so 2 to a little bit more than 3, so roughly about 10 to the 48 or so, which is going to be defensive against a very, very, very large number of messages. So closer to 10 to the 20th, which would take a lot of time and effort to generate. Okay, so that's how the random oracle model works. It, in theory, it works, but it requires that the size of y be very, excuse me, very large, and we can use this formula to estimate what the size of y has to be to make the message system secure. Okay, so let's start actually looking at a hash system here. These are called the secure hash algorithms. They are a set of cryptographic hash functions that are published by NIST. This is the National Institute for Standards and Technology, that is also the publisher of the AES algorithm. And there were 4 algorithms in the system. The first one was just called SHA for Secure Hash Algorithm. Since the later ones got numbers, we sort of now talk about SHA 0. It was published in 1993, but withdrawn very shortly afterwards. There's recognized that there was a problem with this algorithm. SHA 1 was published 2 years later. It corrected the problem with SHA 0. It is now considered broken, and we'll talk about how, what we mean by broken in this case, but it is considered to be a broken algorithm. It is no longer recommended to keep messages secure. SHA 2 is a variation on SHA 1. And in fact, there are 2 different versions of SHA 2 that differ in block size and number of rounds. So there's sort of a strong version of SHA 2 and an even stronger version of SHA 2. We'll talk about those. And then SHA 3 was published recently, 2015, and it's not a modification of any of these previous ones. It is a new type of algorithm. And NIST has deployed SHA 3, but they have not withdrawn SHA 2 because there are a lot of legacy implementations of SHA 2s that are still around. And so SHA 2 is still considered to be a secure standard. We're going to take a look at SHA 1 and SHA 2 over the next couple of days. We're going to look at SHA 1 even though it's broken, because SHA 2 is a variation on SHA 1, so we need to sort of see how this one works to understand how this one works. So we're going to cover both of these over the next couple of days. So let's talk about SHA 1 for a moment. SHA 1 uses a block size of 512 bits. So if the message is longer than 512 bits, it breaks it up into blocks of this size, and if we need to pad the message out with data that generates blocks of 512 bits. It is not super fast. There are 80 rounds of computation for every block. And so that is one sort of limitation of SHA 1. It's not super fast. And when it's done, it yields a digest size of 160 bits. So I've been using 2 to the 160 as a benchmark for some time. That comes from the number of possible digests that SHA 1 can generate. SHA-1 was deployed in 1995. In 2005, so 10 years later, an algorithm for performing a collision attack against SHA-1 was published. This was just an algorithm. At the time, it hadn't been successfully used yet because it requires a lot of computational time. 12 years after the algorithm was performed, 2017, a team from Google actually applied this algorithm to provide two colliding PDF documents. And it used enough CPU time. It was computationally intensive enough that the cost of purchasing that amount of CPU time on like a cloud system like Amazon EC2 ranges from about $75,000 on up, which means when we say that SHA-1 has been broken, it's not broken in a casual sense. It is still computationally intensive to break. That you don't have to worry about, your mom or your best friend, interfering with your SHA-1 signed messages. What you do have to worry about is if you are Walmart, you might want to, worry about a business like Target using, doing something flaky with your SHA-1 encryption, because $75,000 is a lot of money to me or your mom or to your best friend, but it's not a unreasonable amount of money for a company like Target to use if it gives them a competitive advantage against a competitor like Walmart. And so at the big levels, $75,000 is chump change for the amount of for what you might be able to gain from that. But this is still an expensive attack. And again, I don't have any recent data. This is data from about 5 years ago. But I don't think this has gone down by much. So NIST doesn't recommend SHA-1 as a standard. If you have, some really old files that were encoded using SHA-1, they're safe from, small time, folks, but in the corporate world, this is a small enough amount that you would want to protect your messages against it. So this is what we mean by SHA-1 has been broken. It's not casually breakable. There is still a significant cost to breaking SHA-1, but it can be broken, and it can be done if you have enough money to invest in breaking something. So you have to be motivated, but you can do it. But SHA-2 improves upon SHA-1. First of all, it's faster. It actually does the work in fewer rounds. There is a temp variable that is, we'll see how this is computed in SHA-1. SHA-2 slightly modifies that computation. The big difference is that there is a round constant, and we saw a round constant in AES as well. It changes every round instead of every 20 rounds. And so what we saw here was SHA-1 uses 80 rounds, but it only changed the round constant 4 times because it changed the round constant every 20 rounds. And so we could cut the number of rounds in half from 20 to 10, but change the round constant every single round, and now we have 10 different round constants instead of 4. And that will add to the complexity. And so this was a big improvement. And then there's a block expansion. This is like key expansion. And it does the block expansion in a way that creates a little bit more diffusion, so it's more complicated. And so these are improvements into security, and then this is an improvement in the speed. And so we are not going to get all the way through SHA-1 today, but let's talk about the general algorithm. There is some pre-processing. We have to have a algorithm for padding the message out to blocks of even blocks of 512 bits, and we have to have an initial hash that will begin the message, and there's a way of generating that initial hash. And then we go through some processing for each block. There's a block expansion, and then we go through 80 rounds. So we choose a round constant, and then we do what are called choice rounds, then 20 parity rounds, and then 20 majority rounds. We'll talk about what choice, parity, and majority mean in just a moment. And then we do 20 more parity rounds. And then at the end of all 80 rounds of computation, and like I said, these are designed to go very quickly, but it's still, you're doing a loop that goes through 80 times, you get a bit of 160 bits. We're going to add to the hash, and again, adding in this case is XOR. And then if there's a new block, we go back through this again, we go through this again, we go through this again, until we get a digest. Okay? We're going to look at the details of how all these rounds work out next time, but I want to talk about choice, parity, and majority, which are sort of central to them, and they can be covered quickly, and they're not hard to understand. So we have these familiar Boolean operators, and, or, and XOR. So if we have X and Y, and then we have X and Y, 0, 0 gives me 0, 0 and 1 gives me 0, 1 and 0 gives me 0, 1 and 1 gives me 1. Everybody should know that truth table. If we have X and Y and X or Y, everybody should be able to do that table. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. And then X, Y, and X or Y. X, or Y. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So those are the familiar operators that you've seen. And they're binary. They take two inputs and produce a single output. So we take an X and a Y, and then we generate an output. SHA-1 uses ternary operators as well, that you've probably not seen before unless you specifically studied SHA. So there's a third variable here, and then we have the functions choice of XYZ, parity of XYZ, and majority of XYZ. And so we're going to look at the truth tables for these three functions and go ahead and try to wrap things up. Okay? So the choice function, X is the chooser. And the question X is asking is, do we choose Z? And if not, we choose Y. So actually, it's do we choose Y, and if not Z. I've got this backwards. So anytime X is false, we do not choose Y, we choose Z. And then that's the value that we report. We report 0, 1, 0, 1, depending on what Z is. But if X is true, then we choose Y and we report back whatever Y says. So the choice function will either return the value of Y or the value of Z, depending on whether X is true or false. If X is true, we report Y. If X is false, we report Z. So that's how the function works. X tells us which variable to choose, and then we report back that variable. There's no computation there. It's just an if statement and then a return statement. Okay? All right. So that's the choice function. Easy truth table, we understand how that works. The parity function is also supposed to be easy. We just report back whether the total of the 3 bits is odd or even. It's like a 3-way XOR. So 0 and 0 and 0, if we XOR them all together, we get 0. 0, 0, and 1, if we XOR all 3 together, we get 1. 0 and 1 and 1, if we XOR all 3 of them together, the 1s cancel and we get a 0. And then if we have 3 1s, we XOR them all together, we get a 1. That's how this works. And so this is, parity is like a 3-way XOR. And at this point, I think you can probably guess how majority works. Majority actually just reports which bits we have more of. And so if all 3 bits are 0, the majority is 0. If I have 2 zeros and a 1, the majority is 0. And it doesn't matter which one is the 1. 2 zeros and a 1, we report the majority. 2 1s and a 0, we report a 1. And so 2 1s and a 0, we report a 1. If we have all 3 1s, we report a 1. We always report whatever the majority value is. Okay? And so that's how majority works. So in choice, X is a chooser that says, are we choosing Y? And so if X is true, then we choose Y and we report back what Y says. And if it's false, we report back what Z says. Then we have the parity function, which just adds up all 3 values and reports whether the total is odd or even. This is like a 3-way XOR. And then we have a majority function that just reports back which value at 0 or 1 we have a majority of among those 3 values. Okay? So what we're going to do next time, now that we know how those 3 ternary functions work, we're going to walk through like the SHA1 code. And when I say walk through an example of computing a hash out over this algorithm, we're not going to do all 80 rounds. That would be terribly dreadful. But we're going to walk through an example of like what the first of each of these 4 rounds looks like. And then we skip ahead. We'll look at we look at the first choice round, and then we skip ahead to see the first parity round and see what happens. That's the idea. Okay? So, all right, y'all take care. Have a great weekend. See you around.